So I'm going to talk about concrete problem in wave turbulence. It's the wave turbulence. I'm going to describe some progress some work we've been doing with two colleagues, Deng and Fabio Pusateri, who are both here. And so we are looking at a concrete problem. But before I want to introduce the water wave problem, so I'm going to spend a few slides introducing the water wave problem. Just as it's an evolution PD. It's a very important evolution PD. It goes back a long time. It has a long history, and there are many questions that have been raised on this problem. It goes. So it's a free boundary incompressible Euler equation. So the picture is that we are looking at a fluid in some region of the space. And the fluid, it has a velocity, and the velocity evolves according to the Euler equations. The Euler equations being dTv plus v grad v is plus gradient of the pressure. There's a right-hand side, and the right-hand side is just a gravity term that's specific to the wave equation, so to the water waves. The gravity g is a number, it's a constant, and it's the gravity coefficient. Now this is the evolution. There's the fluid, so the fluid occupies some region of space, and the boundary of the fluid evolves as well. And evolves in a way, it evolves in what's called, it moves with the fluid. Gamma t, so the free surface evolves according to the kinematic boundary conditions that it moves with the fluid, so dtz minus the velocity, so the particle on the boundary moves the boundary in its direction. And so dtz minus v is tangent to the gamma. Now, if you want to think how these equations are well posed, it has a complicated theory. It has a rich theory. If you want to think how do these equations even make sense? Why do they make sense? One can think of it in the following way. So if we know the initial state at some fixed time, then we can calculate. We can take the divergence, so the whole thing is incompressible. The divergence of v is equal to 0. We can take the divergence, and if we take the divergence, we can get the pressure. We can get delta of the pressure in terms of the velocity. So if we were to know the velocity, we could calculate delta of the pressure. So in order to be able to calculate the pressure exactly, we need to prescribe the pressure on the interface, which is this last condition, that the pressure is given on the interface by a multiple, which could be 0, and in the concrete theorem I'm going to have is going to be 0 times the curvature of the interface. So these are the equations. So now, if you want to think how do they make sense, so if we know the picture at some fixed time, then you can calculate the pressure the way I said. So we calculate delta of the pressure. Once we know the pressure on the interface, you can calculate the pressure everywhere into the fluid. Once we know the pressure, you can calculate the dTv. So you can calculate, go back to the equation, calculate dTv, so then you can calculate the increment of the velocity, and then we are in the same situation as the initial time. So at least it looks like we have all the ingredients to make sense of the equation. And indeed, this is how it works. So there are lots of questions, and my point is I'm going to talk only about one of them, the last one. But as I said, I want to have a slightly broader picture of what the water wave system is. And so there are lots of questions. There are the usual questions one can raise about any evolution equation. First, the most important one is the local regularity. Can one make sense of the problem beyond the heuristics that I said? So can one make sense of the solution? And there's the local regularity. Another very important question is the dynamical formation of singularities. For the particular problem of water waves, there's a giant amount of literature on steady water waves. And the question that I'm really interested in is the long-term regularity and the asymptotics of the solution. There are variants, so the system that I wrote, there are variants of the system. One can look at periodic boundary conditions in which the bottom, so the parameters are in a torus. One can look at finite bottom, so instead of having an infinite fluid, one can take a fluid with a finite bottom, and then one would have a condition on the bottom as well. One can also look at more complicated two-fluid models, so there are variants of the system. I'm going to say a few words about the first three bullets, just to make sense, just to get some general understanding of the equation, and then I'm going to focus more on the long-term theory, which is connected to the wave turbulence. So this is the plan for the lecture. Now, In terms of local oppositeness, the local oppositeness theory is not trivial. It's not like the local oppositeness of the Euler equations. It goes, there's been a lot of work, and the earlier work, Nalimov, Yoshihara, and Craig, covers some special cases. The work that basically, so the complete theory, the complete local oppositeness theory goes back to work of C.J. Wu from '97. So it's less than 30 years old. That's in the case of irrotational fluids. The solutions don't have to be irrotational, but if they're irrotational, initially, they will stay irrotational. And there's been other theorems. There's also work of Bayer-Günther, Christodoulos Lindblad, and there's a list of theorems, list of people who have worked on this. By now, the theory is very well understood, and it's very simple to explain in just one paragraph. Namely, one has local regularity, so one has a solution on a short time interval, provided that the data at time t is equal to 0 is smooth enough. And there's a certain technical conditions, the so-called Rayleigh-Taylor sign condition, which is automatically satisfied if the surface coefficient is strictly positive. What's more important is the time of existence. So the time of existence of solutions that we start with, it's very natural. It depends, first of all, on the smoothness of the data. So you need the data to be sufficiently smooth in order for the equation to make sense. And it depends on one more piece of information that, if I had a board, I would draw the picture. It's the so-called Arcourt constant of the interface. The picture is that if you are to have a fluid that almost self-intersects, so you can imagine that you have a fluid that almost self-intersects at the initial time, then the fact that there's an almost self-intersection of the interface at the initial time, that gets reflected in the length of the time. The time of existence will be short, because otherwise it would self-intersect very quickly. So these are the parameters that come in the local oppositeness. Another question I'm not going to talk about, but which is also very important, is formation of singularities. Of course, there are two possible types of singularities. There is singularities inside the fluid, and that question cannot be resolved without understanding singularities for Euler, because if anything, you have less control than for the Euler equation. The problem is only harder than the Euler equation. But there is one other way of producing singularities, namely an interface singularity. And so there's some work in that direction. There's a so-called splash singularity, which is the picture that I described, that one has a fluid that's almost self-intersecting, and by arranging the initial data in the right way, one can make sure it self-intersects in finite time and control the solution until that. So that's the so-called splash singularity. It's a splash singularity so this was found. This construction was performed by Castro, Cordoba, Pfefferman, and Pfefferman, Gancedo, and Gomez Serrano, and then by Coutin and Scholler. These are separate papers. It turns out that this splash singularity, it's not quite as robust as one would like, because it cannot happen, for example, in a two-fluid model. So if you were to have a fluid and vacuum, it could happen, but not in a two-fluid model.
You mean two incompressible fluids?
Yeah, two incompressible fluids. What would be a very interesting problem, and I think it would be very interesting in many ways, is to see if, even at the numerical level, to understand good numerics for that, is to show loss of regularity of the interface, namely the fact that the interface can start smooth and can produce a corner, let's say, in finite time, maybe a corner and self-intersection at the same time. So this is an important open problem. So this is a very quick review of the theory of the formation of singularities. Very little is known other than this particular splash singularity that can happen in the case of the water waves. And the last topic in this general discussion concerns a very interesting family of problems. This is more specific for waterways. The other two are very general problems. You can state them for any evolution equation. It's something more specific to water waves, and it goes back to work of Stokes for more than 150 years ago. So it's a very classical problem, namely understanding traveling waves. So this means steady solutions which don't change shape. They could be traveling, they could be steady, they could be periodic, they could be infinite, they could be in the Euclidean space. And the construction of these problems, the stability, one can also raise questions about the stability. There are beautiful open problems about the stability of these steady solutions. Most of them are not stable. So even the most famous ones, like the Stokes waves, they are not stable. So most of them they are not stable. There are also questions about the overheading, the shape of these profiles. And so there's a large amount of literature starting with Stokes from 1947, and it's still a topic of interest today. Now, my question, the question that we'll be mostly interested in is the question of wave turbulence. Now, I'm a pure mathematician, so it's very important to be able to state theorems. In order to be able to state theorems with hypothesis and conclusion, I'm going to talk about, so the general question is wave turbulence, and one can look at this in many ways. I'm going to pick only one way to look at it, namely through the time of existence. So to me, almost everything has to do with how long of a time can you control the solution for. With understanding that if you control it for a long time, then one can, controlling for a long time is, in my mind, almost equivalent to understanding the full theory. It's hard enough to control the solution for a long time. So that's the point of view I'm going to take, mainly because I want to have some simple theorems I can state. So now there's been some work done on long-term and global regularity of the water waves. And now the work that, so the more conclusive work, the global solutions, it's very hard to construct global solutions. So the global solutions, they are constructed through a different mechanism than the mechanism I'm going to talk about. They are constructed through a so-called mechanism of dispersion. I'm stating them here just because, just to have some references, but the two bullets here, the ones that mostly going to be connected to what we do is the second bullet, the so-called the periodic case. So in the Euclidean case, in the Euclidean meaning that in 2D and 3D fluids, meaning that one is looking at 1D or 2D interfaces, there are some global solutions. They're only in very specialized scenarios. So all the global solutions, they're only in the case, in the irrotational case. So global in time, in order to have global in time, you need to be in the irrotational case. You also need to be on the real line. And one can have, there are two parameters, gravity and surface tension. I can also take parameters in terms of the finite bottom. So there are some theorems of this type. And they are not very old, so they are pretty recent theorems, starting with work of C.J. Wu and work of German Masmoudi and Chata, and work that I've done with Fabio Pusateri and with Deng. And so there are several papers that I wrote there that give prove that in certain situations it's possible to construct global solutions. The mechanism, as I said, has to do with one has to start to localize initial data, and the mechanism is a mechanism of decay and dispersion. What's relevant here, what's more relevant for what we do, is the periodic case, in which it's very hard to produce global solutions. Not known how to produce global solutions in the periodic case because the basic mechanism of dispersion does not. There's no decay in the periodic case. But in that case, one can look at the question of long-term solutions, and we've seen on Monday the lecture of Massimiliano Berti, so on this paper of Berti, Maspero, and Morgante. And there are other results in this direction, basically saying that under some algebraic assumptions that essentially have to do with the resonances, one can construct long-term solutions of certain waterway systems. In their problem, they needed what's called exterior parameters in order to be able to satisfy the non-resonant conditions. So that's the. So now you're getting closer to the topic of the lecture. Now, we are only going to talk from now on about irrotational waterways because that's the only ones for which you can construct these long-term solutions. The irrotational waterway system, it's obtained in the following way, can be derived easily from the original system. So one is looking, so to get more concrete to the theorems, we are looking at a large box, the large box being in terms of a big torus of radius r, in d dimensions, let's say. D is going to be 1 or 2. And we consider irrotational flows. And then we are looking at the velocity potential, so because you're in the irrotational case, we can talk about the velocity potential. So the function capital phi is the velocity potential. And then we are looking at the function little phi, which is the trace of the rotational potential on the interface. And that turns out to be the right variable to consider in order to state the system as economically as possible. And so there's a way to basically reduce the entire system to just something about these two variables, h and phi, which are functions that are real valued on the torus. And it's a classical formulation in Eulerian coordinates. We have two equations for h and phi. First of all, dth is equal to gh phi. Gh phi is the Dirichlet-Neumann operator. It's a renormalization of the Dirichlet-Neumann operator, which takes a function phi. It's a linear operator in phi and non-linear in h. It takes a function phi. It does the extension given on the bound. It does the harmonic extension, and it looks at the derivative, the normal derivative of this function. And so there are two equations. Dth is equal to gh phi, and dt phi is a combination. It's a slightly more complicated combination. Each one we are looking at one linear term. The first minus gh, and then we have minus sigma times the divergence of essentially some kind of Laplacian of h, and then two nonlinear terms coming from the velocity terms in the original equations, which are in terms of grad phi. So the last two terms come from the quadratic velocity terms in the equation. So this is the Zakharov formulation. It's a very classical formulation. We've seen it in other talks on water waves. It's very useful. It's economical in the sense that it's the smallest number of variables you can have. It depends on, it's a little implicit because it depends on this function gh phi, but we have a pretty good understanding of gh phi, particularly in the case of small. So you're going to think of h as some kind of a perturbation of the flat interface, so it's going to be small. So particularly in these cases, we have a pretty good understanding of gh phi. Okay, so this is the system that I'm basically mainly going to refer to. The system, it has a conserved Hamiltonian coming from the original L2 conservation of the velocity. It's a conserved Hamiltonian. Each one we look at the integral of gh phi times phi. That's the kinetic energy. We have the potential energy due to the gravity terms of the second term. The second and the third term, these are the potential energy depending on the gravity and the surface tension. So we have this. So we have a Hamiltonian system that can be written in this way. Now, the question that we are looking to understand is there's an outstanding problem here that goes back to Hasselmann and Zakharov from the 60s. The question is to understand wave turbulence of water waves, meaning to understand the wave turbulence theory for this system. It's a key part, so the reason why this is important, it's a key part of what's called Hasselmann's model of climate variability. So Hasselmann started this in the 1960s, and by now it's a central model in climate studies. Now, Hasselmann got the Nobel Prize for this, so there are lots of other people who contributed. Hasselmann is the one who got the Nobel Prize, so many of the things are put under his name. There's one other person that definitely needs to be mentioned, at least as a mathematician. I think Zakharov had a major contribution to understanding these things, so I call it, so this is, and he worked on this slightly later than Hasselmann, a few years later. And so this is based, so the question is to understand, to make sense, to make sense of the wave turbulence theory for water waves motivated by understanding this climate variability. Now, as I wrote here, the wave turbulence problem has received intense attention in recent years, mainly in the context of semi-linear dispersive models such as the Schrödinger and KdV equations. And there are several people, part of this collaboration, have worked on this, and we've seen lectures on this before: Buckmaster, Germain, Hani, and Chata, Deng, Hani, Colo, Germain, and Tran and Stafilani, with the goal being to derive the wave kinetic equation. Now, when we look at it from the point of view of water waves, the question is too complex. And I somehow don't, I'm not even sure I can ask the right questions exactly how I can have a good formulation of the problems. So as I said, I'm going to think the way we are looking at it from a mathematical point of view. For me, wave turbulence means understanding the time of existence of the solution. So we start with initial data that we have some parameters, like for example, we can have the size, the epsilon, the size of the solution, and we can have the parameter r, the parameter of the torus. We can have randomness, and basically want to understand to what extent is randomness helping extend the time of solution of the equation. So at the analytical level, we are not going to look at exactly the wave kinetic equation, but we are going to look at understanding dynamics of solutions corresponding to randomized initial data in a large box, and the point is on long time intervals. So the longer the time intervals, so the long time intervals is where the difficulty is. Now, so I'm gonna state two. As I said, I'm a mathematician, so I want to state exact theorems. I'm going to state two theorems in very soon. But just to compare, just to motivate the reason what we are trying to do and why is it that. So what it is that we need to understand, I'm going to compare very briefly with the theory that one can do for the cubic NLS, which is by now well understood due to work basically of Deng and Hani. And so for the cubic NLS, one is looking at a simpler model. So IDT plus delta U is U times U squared on a torus of radius L. And one is looking at solutions U that start from so the point is the initial data. The point is this type of initial data, which is so the initial data is randomized, and then one is looking to understand the frequency amplitude of u hat of tk of the absolute value of u hat of tk squared, and the point is to understand to be able to track this related to a solution of a kinetic equation. In some sense, to derive the kinetic equation and to track these two objects in parallel. And the only way to do it is to, the main thing here is there's only one thing that really matters here, which is this so-called T kinetic, which is lambda to the minus 4. So there's only, this whole slide, there's only one thing that is really, that's really important, which is the length of the time, the kinetic time on which one can prove control of this frequency envelopes, of these frequency amplitudes. So that's so one can look at the problem this way. Even in this case, one can ignore. So if you want, you can ignore, for example, one can also state the question even at this level of understanding the time of existence of the solution. Now, time of existence, because the cubic NLS. Time of existence actually means time of, let's say, on how long of a time one can control a high Sobolev norm, because otherwise it's too simple. But a high Sobolev norm on how long of a time one can control, one can make sense of this question independent of whether there is or there is not a kinetic wave equation. Now, the main idea, in order to be able to hit the whole point, as I said, is the lambda to the minus 4. The main idea is to expand the solution, and there is the Duhamel expansion of the solution. One can start with u of t is e to the it delta phi, so the free evolution of the initial data, plus the contribution of the contribution of the nonlinearity, which is minus I times interval from 0 to t of e to the I t minus s delta times the nonlinearity at the point s. So this would be the first expansion. Now, in order to be able to understand the solution, one has to keep expanding. So one has to keep expanding u, so then afterwards one puts u in terms. So one puts u again in this formula, one gets something just in terms of phi. Now, as a PD person, it's a little, this feels a little strange that you'd be winning something by doing these expansions, because of course you lose lots of information about the solution. It turns out there is one piece, you lose lots of information, but there's one piece that one can track with this expansion, namely the randomness. At the end of the day, there's only one hypothesis stronger than everything else, which one has to track, the randomness of the initial data. And the only way to keep track of the randomness is through this expansion. So that's the reason why one is actually forced to do the expansion. Now, what we like to do is to initiate a similar investigation for irrotational waterways. However, there's a fundamental issue at the very first step, namely that waterwaves cannot be described even in the small initial, even if you're just thinking of small perturbations of the flat state, one cannot. These are quasilinear equations. I cannot describe them in terms of the Duhamel formula. There is so even one can do formally and can write formally the solution in terms of the initial data plus some kind of contribution of the nonlinearity, but there's a loss of derivative in the nonlinearity. So there's a loss of derivative in the first Duhamel formula. If one is to expand the Duhamel formula again, there'll be another loss of derivatives. So then at every expansion, you lose derivatives, and there's no way to close it. Even at the local level, one cannot make sense. Even up to time 1, one cannot make sense of the formula even up to time 1. There's no, and that's, so one has to imagine a different scheme, essentially, because one cannot use this basic starting point. So as I say here, the solution cannot be described using iterations of the Duhamel formula, and which are called Feynman trees. And so to address this issue, we propose a new mechanism based on a combination of two ingredients. And we have I'm going to state two theorems. Eventually, I'm going to state, in the next 15 minutes or so, I'm going to state two theorems. But here I'm just describing what the two theorems do. So there are two ingredients that we need to exploit. First of all, we need to do energy estimates. So we prove first energy estimates on the increment of the highest order derivatives of the solution. This is a step that's needed even for the local theory. Just to go from time 0 to time 1, you need to close with energy estimates. These are deterministic estimates. So unfortunately, we are not able to do energy estimates at the highest order to distinguish between deterministic and probabilistic estimates. And so the increment is controlled by an L-infinity based norm of the solution. So the key point is to show that the increment of energy is controlled by an L-infinity norm based L-infinity based norm of the solution. And at that level, for the L-infinity norm of the solution, which is at the lower order of derivatives, we can start using randomness. So that's the first step. We need to prove these energy estimates. And the second step is to try to propagate randomness, because at the end of the day, you can also see the whole problem as a question of can one propagate randomness. And the second step, we are trying to propagate randomness and pointwise bounds. So we are proving propagation of randomness in a suitable norm. And for this, because the second stage, because you already have control of the highest order of derivatives, we are allowed to lose derivatives. We are allowed to lose the Duhamel formula losses of derivatives and try to close that way. So this is the plan for what we want to do. Now, of course, the result is going to be weaker. So I'm going to say it right now. The result is going to be weaker than one can get. Whenever you need to close through energy estimates, the result is weaker than one could get for the cubic analysis. It's the same situation if you want to think in terms of the deterministic problem, not the probabilistic one. The deterministic problem for the cubic analysis, because one can use the Duhamel formula for the same reason, basically, because one can use the Duhamel formula. For small data, one can prove global regularity in a pretty. It goes back to work in the 80s. So it's a very essentially because one can use the Duhamel formula, one can use Strichartz estimates, and one can develop Gigliola knows this very well. One can develop a very complete theory for the cubic NLS. For the water waves, even in the deterministic situation, the situation is much harder, exactly for the same reason. One doesn't have an expansion of the solution. So these are the two theorems that I want to state. So the concrete results are the following. So I'm going to talk only about one model, which in retrospect is not the best model to study. It's kind of like the most classical model, in which one is looking at gravity water waves. In retrospect, it's not the best model. So, but this is the one that we started with now, before knowing that one can do better for other models. So the theorem is the following. So the first theorem is the following. The first one is the energy estimate, which is what we call Quintic energy estimates. So we are looking at the case, we are looking at water waves in 2D. Water waves in 2D means 1D interface. So 1D interface, and gravity means that we are only fixing, we are only looking at, we are looking only at gravity, so sigma is equal to 0, the surface tension coefficient is equal to 0. And they are saying the following, so you're looking at the solution of this system, this is the system that was written before in the case when sigma is equal to 0. And we assume that we control, on a time interval, we assume that we control a high energy norm, and we assume that we control an L infinity base norm. Omega, it's a technical variance. So it turns out that one cannot work exactly with the variable phi. One has to work with the variable omega. That sometimes has to do with loss of derivatives. But one should just think of phi and omega as being interchangeable. So these are the assumptions, that we control the energy and the L infinity norm on this time interval. And then the conclusion is that we can control. So the conclusion is that we can control the energy at the final time in terms of the energy at the initial time plus a Quintic contribution. So here we have the energy, A is the energy, but the increment is measured by the cubic power of the L infinity norm. So this is what I mean by. It may look a little technical, but that's the kind of thing that we need. We need various combinations of norms. The L2 norms, the best we can say they are controlled. The L infinity norms, we want to be able to use smoothness. We want to be able to use randomness. What was I saying? So that's so the point here. The main point here is the increment. So the way the increment is measured. In terms of the cubic power of the L infinity norm. So it's the L infinity norm that can be small. The L2 norm cannot be small. The L infinity norm can be small. So that's the one that we want to use here in the right-hand side. So the point is, so as I say here, the point is that the energy increment is Quintic. And moreover, it involves the energy itself as a square. The square is because we have everything here. The energy is, everything is squared. But what really measures the increment, the L infinity norm, is the cubic power. And as I said, it's important to distinguish between things that are in terms of the L2 norms, which cannot be small, and things that are in terms of the L infinity norms, which are the ones that we want to get small. And then, so the main novelty here in the theorem is the cubic, is the fact that we have the power 3 here. The theorem had been known with the power 2. That's the usual quadratic energy inequality, and that can be proved going back to work of C.J. Wu. So that's known, but the main result here is the cubic, the cubic growth here. So that's one of the remarks that I had. And now I'm not going to describe too much about the proof of this theorem. I just have a few remarks to put things in the right context. And how do we get the Quintic? How do we get the Quintic energy inequality? We get the Quintic energy inequality because we can analyze the resonances. So the basic issue, we can analyze the resonances. There are two types of resonances. There are the quadratic resonances. So at the linearized level, the equation can be written in this schematic form. dt plus I dx to the 1/2 u is a nonlinearity of u. And it turns out that the quadratic resonances can be removed. So one can look at the quadratic resonances can be removed simply because there are no three-wave interactions for the gravity water wave system, and that has to do with this algebraic fact that it's not possible to this algebraic fact that it's not possible. There are no three waves interactions in the gravity waterways. This algebraic fact, in fact, implies that one can perform a normal form, and one can prove a quartic energy inequality. So that's in order to perform for the first step. Now for the second step, we need to look at the four-wave interactions. And so the four-wave interactions are more complicated. There are two types of four-wave interactions that could, in principle, lead to resonances. They are the so-called trivial ones, and they're the Benjamin-Fair ones. They are resonance, and they do contribute into the system, but not at the energy level, because at the energy level there's a symmetrization, and the trivial resonances are removed. And then there's a miracle, there's the algebraic miracle, that even the so-called Benjamin-Fair resonances are also removed. The Benjamin-Fair resonances are more complicated resonances, They have this type C1 is lambda b squared, C2 is lambda b plus 1 squared, and C3 is some other combination. So there's a two-parameter family of Benjamin Fair resonances, but they are multipliers in the problem. It turns out that those multipliers vanish exactly on this two-dimensional manifold of Benjamin Fair resonances. So this is a very important observation that goes back to Dyachenko and Zakharov, and that led, at least for a while, people thought that maybe there is some kind of complete integrability in the system. It turns out it's not. It's only at the level of the quartic of the four-wave interactions. But in any case, so there is this algebraic fact that the multipliers vanish on this Benjamin Fair resonances, and this leads to, so our main contribution is to show that one can perform the normal form, which formally can be done because of this fact, but one has to do it without loss of derivatives and control the energy this way. So these are, so this is the Quintic energy estimate. Now, as a first application, without randomness, still without randomness, but just from the Quintic energy inequality, we can prove the following. So we can prove that if we are looking at initial data, so without using randomness, it's kind of like a corollary of the theorem that I had. Without using randomness, we can prove that if we are looking at initial data of size rho in the energy space, then we can construct a solution on an extended time of existence, and the time of existence is the one written here, so it's rho to the minus 3. When R is large enough, if we think of the regime when R is large enough, it's rho to the power minus 6. So that's so there's an extended time of existence on which you can construct the solution, and that's so this is a corollary of the theorem that I just discussed, the energy theorem. Still, we don't have randomness in the problem. And here to compare with some of the literature that was there before. So in the case of the fixed torus, R is equal to 1. Now, when R is equal to 1, the time of existence turns out to be rho to the minus 3. That's the minimum that so the minimum becomes rho to the minus 3 there. So in the case of the time, so in the case when R is equal to 1, so on a fixed torus, one can recover the time of rho to the minus 3 that was proved before by Berti, Feola, Pusateri, and C.J. Wu. And as I said, the result is probably optimal because there are resonant 5 waves. When R is large, so in the Euclidean case, for example, we get this very long time of existence, rho to the minus 6. That's an improvement of all the previous results on the Euclidean case. Now, in the Euclidean case, as I said, in the Euclidean case, but by a different mechanism, one can prove global regularity, but in order to prove global regularity, one needs localization. And localization is not compatible with randomness. So it's not possible to have both localization and randomness. So that's why, so that's the last remark here, that in the Euclidean case, one can prove global regularity, but only by localizing the initial data, which is not compatible with what we want to do, namely the random theory. So this is the theorem, and so the proof is actually not, the proof of this theorem is not hard. I just need to bring it up here because it's there's one idea that we use here and we use in many other places, named this what we call the Z-norm method, which is that we have to define a certain norm that captures the problem, and that's the norm that we can propagate through the flow. It's a non-trivial norm. It's not about L2. It's not about energy norms. It's a different norm. In this case, I wrote it here. It's simple enough to write it here. We look at an L4 in time and L infinity in X on certain time intervals of suitable lengths. And that's the norm that we use in order to, in conjunction with the energy norm, in order to be able to close the bootstrap argument. So it's a Strichartz norm. It's basically a Strichartz norm it comes from the L4T L infinity X Strichartz norm, which is a way to it's in some sense a better it's better than using Sobolev inequalities. Okay, so the final theorem that I want to state is about random initial data. It's the theorem that it's what we see is as the closest variant to the closest to getting to the wave turbulence. So here I just rewrote the system to remind the system. We were talking about the 2D rotational gravity water waves problem. it's a system in dt agent, dt phi. Now we can also write it as a complex, one variable complex system by looking at u is equal to h plus I dx to the 1/2 of phi. So that's so then it becomes dt of u. So it becomes an equation for dt of u. And they are looking at a torus of radius r, and they are looking at random initial data size epsilon. Size epsilon is at the level of L infinity. So the way the formula is written for u, we are basically looking at randomized initial data, and the way the epsilon r to the -1/2 come, so that's in such a way that the L infinity norm is of size epsilon. So we're looking, of course, so all of these coefficients, eta k of omega, these are independent random variables. And the theorem, so I'm going to state a theorem we have in this case. And we are thinking of the case when r is very large, epsilon is small, and the link is the usual link r is epsilon is equal to r to the minus alpha. But one should think of alpha as small. In order, as I'm going to explain, it has to do the number theory of the problem that one needs to have alpha to be small. And this is the second theorem. So the second theorem is again a time of existence theorem because I'm using this as a proxy for wave turbulence. And what we are saying is that if we are in this scenario, and if the initial data is of the type that I had on the previous slide, then one can control the solution almost surely, so with probability almost 1, on a time of existence of size epsilon to the -8/3, almost epsilon to the -8/3. I'm going to try to explain what this comes from. So so we control the solution on this time of existence. So I'm gonna have a few bullets of how we get there. One should compare. So this is the time of existence epsilon to the -8/3. It's a weaker time of existence than one would get, for example, for the Schrödinger equation in high dimension. Even for a Schrödinger equation or similar equation in one dimension, one doesn't get a very good time of existence, but what one would really like to have is epsilon to the power -4. That would have been the kinetic time. Now, so the randomization of the data, this is the theorem. The randomization of the data gives enhanced control, as I said, on L infinity type norms. Basically, because in the process of proving the theorem, we need to show that we preserve randomness. And if you are thinking of random objects, the L infinity norm and the L2 norm, they are connected by this relation that epsilon is a times. So the L infinity norm is the L2 norm times r to the power -1/2. So this is the theorem. Now we still need to use, the only way to get such a long, it's still a pretty long time of existence. The only way to get a long time of existence of this type, we still need to use all the machinery that has been used for the cubic NLS, including Feynman diagrams. The point of Feynman diagrams, you need to get a square root cancellation. There's a key. Everything hinges on being able to get the square root cancellation first, and so that's how we do this by using Feynman diagrams. Okay, so this is basically the main. So this is the main theorem that I stated here. So the point is that one gets a time of existence, time of control of the solution of epsilon to a certain negative power. And now I'm going to explain a few bullets of. So I'm going to provide a few. I'm going to give a few ideas of what to use. So look at this truncated equation. So formally, we look at the truncated equation, and we perform. So we perform a normal form.
Is that the initial datum can have a large Sobolev norm, but is small in L infinity.
Yes. You need the time of existence to depend only on the L infinity norm. Yes.
Because if the initial norm, if the Sobolev initial norm is smaller, you have epsilon -3 of the deterministic case.
The point is to get the time of existence depending only on the L infinity norm. The L2 norm could be very big, of course. Okay. Yeah, the point is and that's why you need this whole theory with the Feynman diagrams and the square root cancellation. Everything starts from there. Okay, so we are comparing the equation with this so-called truncated equation. The way we get the truncated equation, the formal level, we first perform a normal form to eliminate the quadratic terms, and then we also eliminate all the higher order. So truncated means that we cut all the frequencies, and the cut is at the type R2. So R is the size of the torus to a very small power. And so we are comparing the two solutions, the solution of the original equation, the solution of this truncated equation. And then we have a proposition that basically if we control the truncated, so the proposition is that basically the two solutions are close by. It's a little more technical to read, but the two solutions are close by, provided that we control the time on whatever time we can control the L infinity norm of the truncated equation. The two solutions are going to be close by, the solution of the original equation and this truncated equation. And once we have this proposition, so the main issue is to construct solutions of the truncated equations on times of existence epsilon to the minus. This should have been minus 8/3. And for this, we'd like to use Feynman diagrams and to expand this if we are looking at the cubic NLS. And now I have a few. So if we are comparing these two equations, just to understand, if we are comparing these two equations, dt plus I dx to the 1/2 W is equal to, let's say, a cubic formula of W, and the cubic NLS dt minus I delta is minus I u bar, u squared. So I'm going to try to compare them and to understand the several issues that come up. First, the loss of derivatives, because of this truncation, the loss of derivative is small, and then we are not going to be anywhere close to the endpoint. So the loss of derivative is not going to play a role to understand the truncated equation. Now, the second bullet is important because it has to do with the number theory of the problem, and that's something very general. We are looking. So our linear dispersion in our problem is c to the power 1/2 as opposed to c squared, and understanding how, for example, equations, even inequalities in terms of square root of integers, that could be that's very tough, and we don't know how to do it. So basically, what I mean to say is that the number theory of the problem could be either very easy or very hard, and one can think that basically we need to understand various sets in the space. And if you're looking at various sets in the space, let's say in 2 dimensions and 3 dimensions, we want to count how many lattice points do we have in these sets. Now, if the sets are thin, this could be very hard because you don't know how to, you can't tell, it's hard to tell that the solution is going to be an integer or not if the sets are thin. And that's what we want to avoid. On the other hand, if the sets are thick, and if they're thick in all the directions, then basically the number of lattice points is the same as the number, it's proportional to the number of, to the volume of the set. And that's the situation we want to be in. In order to be in that situation, we need the time of existence, because the frequency is moved by 1/r, and it has to be that the uncertainty principle, which is the time given by the time of existence, is better than that, which is a certain connection between the time of existence and r. It has to be the time of existence is smaller than r, and in this case, we're able to avoid the number theory. So that's one of the restrictions, and that's a general fact. So if you are looking at, one could have put any dispersion relation here, unless you can do number theory for that dispersion relation, which is quite hard for, unless it's like a square or something like that, then that's the kind of restriction one needs to have. Now, there are a couple of issues that I want to bring up. Namely, for the cubic NLS, one can have resonances. One has to look at the basic, the trivial resonance. One has to remove them. It turns out that in this case, it's in the case of the water waves or for many other equations, there's no simple way to remove them because the renormalization, it's a complicated renormalization one has to do in order to remove them. It's not in terms of a constant like an L2 norm. It's something, this function, the renormalization is more complicated, so we need to have something that depends on the time and on the frequency. And one other difficulty has to do with randomness of the. So one other issue that we have to understand, which is basically which I feel like we don't understand it well, is what are the right variables. So one can look, for example, at so the variable that we want to work with is this normal form variable W, but the variable for which we have randomness is the original variable U. And they are related, but they are not, so knowing that U has randomness doesn't mean that W has randomness. So in order to be able to work with this situation, we need to, we actually need to redefine the notion of a tree. We define that the trees can have two types of nodes. They have nodes that are from the interaction nodes and nodes that are related to the normal form, and we have to develop the theory in that way. Basically coming from the fact that the basic variable we want to work with, the cubic variable, does not have the right randomness in it. Now there's one other issue that I didn't bring up, and it's something that we are not aware at the beginning, namely that the analysis in dimension 1 is pretty tough. It has to do with some counting estimates that don't work out the right way. And even for the MMT case, which is a semilinear equation with fractional dissipation, like let's say c to the power 1/2, there's not a resolved issue. So the understanding the right time of existence for in one dimension, it's not resolved. The best result so far was a result of Katya Vasilev, who proved the time of existence of epsilon to the -5/2 in the situation that I mean it would have been epsilon to the -5/2. And this is the last slide, so the conclusions. The wave turbulence theory is it's wide open and pretty tough, but of course this is the main open problem connected to the Hasselmann theory. There's one central difficulty in the beginning, namely the fact that it's a quasilinear model, so the Duhamel formula cannot be used. There's one other difficulty that comes up, namely that what ends up as the formal equation itself is not well posed because there are multipliers that come in there which lose derivatives. And what we do, because we don't understand many of these issues, is we use time of existence as a proxy for the wave turbulence theory. And this allows us to avoid, it's a robust way to avoid a bunch of issues that I don't know how to answer, namely what are the canonical variables to measure and how to look at them. Thank you.